Okay, here I'm going to present material from Chapter 3 on dispersion and pulse spreading. And here what we're going to do is we're going to go into more detail about the effective pulse spreading and actually quantify that, the upper limit on pulse spreading for a communication system with a given bit rate R. And what we'll do is basically just draw a bunch of pictures to give you the idea, and then write down the corresponding equations that we'll use as we solve problems, and that will guide us in our understanding of how pulse spreading affects our systems. So what I'll do is I'll start with a sort of a picture of a little chunk of square wave as an input to a fiber. You know, maybe this represents a 1, 0, and a 1 on an on-off keyed system. We're going to go into the fiber here, and we know that we have dispersion, and so at the output we're going to get two superimposed, spread out pulses here on the output side. And so this is the input, and this is the output. And the question is then, on the output side, we have a 1, and then we have a question mark, and then we have another 1. So we have intersymbol interference going on here. And we've already talked about the fact that pulses do spread out, and so we quantify that by drawing this pulse in time as having some width characteristic of the bit rate of the system. So we'll call that TB, the bit period. And on the output, so this is the input, and on the output we have in time a wider pulse of width T, the bit rate plus delta tau, as we're going to call it. And delta tau is referred to as the pulse spreading. It characterizes what's going on, and it's measured typically in picoseconds. Okay. The thing to notice is that delta tau is proportional to the distance traveled in the fiber. And this is sort of intuitive. We're not going to prove it. Is proportional to the distance traveled in the fiber. And you can sort of draw a picture of this, I guess, where you have this fiber here, and on the input you've got a single pulse, and the idea is that, at least schematically, that different spectral components of this pulse are traveling at sort of different rates. So we have maybe the red end of the spectrum and the blue end of the spectrum, schematically at least. So we got them going together at the beginning, and one side of the spectrum goes a little bit slower than the other, and it really is just due to different spectral components going at different speeds. And here, well, the difference in the propagation speeds builds up over time, clearly. So this is the sort of the cartoon picture of how this happens, where if we go 2 times the distance, we get 2 times the pulse spread. Okay. So what we do is we characterize the pulse spreading. We don't want the pulse spreading to be dependent on the distance we've gone. We want to characterize the fiber. We don't want to worry about how far we've gone in that fiber. So we write delta tau by L. Okay, where L is now the distance in the fiber, usually given in kilometers. Delta tau by L is the pulse spread. Per unit length. And so this is going to be the important quantity, and we're going to measure this in picoseconds per kilometer. It's possible to measure it in seconds per meter or in inverse velocity, but picoseconds are the characteristic size of pulse spreading, and kilometers are the characteristic size of the lengths of our fiber runs. Let's take this and apply it to a communication system now. So how much pulse spreading is too much? And the answer is it depends on the bit rate of the system. And so what we're going to do is we're going to say that the approximate condition well, you can see from this figure up here that essentially what we want is we want to make sure that the pulse spreading is somehow not causing intersymbol interference. And so what we want is we want the pulse spreading to be less than a bit period. And what we'll do is we'll go ahead and we'll say that the approximate condition that we're going to use for an acceptable pulse spread to avoid intersymbol interference is that delta tau be less than or equal to the bit period over 2. Okay. In terms of the bit rate, which is the inverse of the bit period, the bit rate should be less than 1 over 2 delta tau. And now we're on our way to seeing the bandwidth distance product, because instead of delta tau, we're going to consider delta tau by L. If we write delta tau divided by L here, that means on the right hand side we've multiplied by L, so we'll also multiply on the left hand side by L, and we get RB times L is 1 over, or less than or equal to 1 over 2 delta tau by L, like this. And so our pulse spread per unit length is inversely proportional to the product of the bit rate and the distance traveled. So this is our bandwidth, or our rate distance, sometimes called the bandwidth distance product. Okay, and for a constant delta tau over L, that is for a constant pulse spreading in the fiber per unit length, that's more or less a constant. And so this is a very important fundamental relationship that characterizes the trade-off between high bit rate and long distance in communication systems. Okay. What I'll do now is just write down the equations that do give the pulse spreading in terms of the material dispersion, and I'll do this really just writing it down. And the important thing to remember here is that even though this picture of twice the distance giving twice the pulse spread, thinking of the two spectral components going at different speeds, even though that is a very nice picture to have in our heads, we cannot simply apply that picture to calculate pulse spreading. It just doesn't work, and it's tied up with the fact that we've got a group velocity with our pulses, and it's much more than we're going to do in this course. But the analysis shows is not based on simple propagation speed differences. the result of the correct analysis is as follows. It shows us that delta tau is equal to minus L lambda all over C, the second derivative of the refractive index with lambda, delta lambda. Okay, so we've got a lot of quantities here, and we're going to simplify this by writing this as minus Lm delta lambda. The minus sign means that longer wavelengths, let's see, I guess effectively travel slower through the medium. I may have that upside down, I'm not sure. It doesn't really matter, but the sign is indicative of the fact that it's either longer or shorter wavelengths are going faster or slower. And M is called the material dispersion. And it is lambda over C, second derivative of n with lambda squared. So the whole origin of pulse dispersion, recall, is that different wavelength components of that pulse are traveling at different speeds. That is, the index of refraction depends upon lambda. Okay? And so here we have that lambda dependence of the index of refraction. If n were a constant, then the delta tau would be 0. If n did not depend upon lambda, delta tau would be 0. And so this is how we characterize our optical fiber. And this is the effect of the actual silicon oxide, n as a function of lambda behavior. This is the dispersion of the glass. Okay, thanks.